Welcome to the Deep Dive. Today we are tackling one of the most frustrating performance issues in modern AI, the cost of consciousness.
That's a great way to put it.
We all know that chain of thought prompting, or COT, is just brilliant. It really revolutionized large language models by forcing them to think step by step.
Yeah, it turned them into these powerful multi-step reasoners.
But, and this is a huge but, if you've ever tried to run a COT model at scale, you hit this overthinking problem.
Oh, definitely.
You ask it for a simple calculation, and the model writes, 5 paragraphs explaining its entire journey to the answer.
It's an unnecessarily verbose output that just balloons latency and, of course, token consumption. It makes deployment incredibly expensive.
Exactly. If you ask a big reasoning model, what is 2 plus 3, and it writes you a short story, that is money straight out of your pocket.
And that's the critical bottleneck for any real commercial deployment. The typical approach to solving this has been what you could call long to short.
Okay, what do you mean by that?
Well, the model generates that long reasoning trace first, and then engineers try to, compress it after the fact.
So things like prompt engineering, where you tell the model, be concise.
Precisely.
Yeah.
Or other methods that fine-tune models to shorten the text they've already produced. But all these methods are fundamentally trying to clean up a mess that the model was explicitly trained, or at least allowed, to make in the first place.
It's a reactive approach.
It's totally reactive.
And that is exactly why the new framework we're diving into today, called 3TF, that's thought training and thought-free inference, is so compelling.
It completely flips the entire paradigm.
Instead of that long-to-short compression, 3TF takes this asymmetric short-to-long perspective. It tackles the problem at, the fundamental level of how the model learns. So the big question is, how do they pull off this magic trick? How do they teach the model to think deeply during training, but then enforce silence and just deliver a concise answer at deployment?
Getting both that high accuracy and massive efficiency.
Yes. That's our mission for this deep dive.
Well, the answer really lies in decoupling the process. You have two very distinct phases here, and they're critical to understanding how this whole thing works.
Okay, let's break them down.
First, you have the training phase. They call it thought training. This is where the model is just fed this incredibly rich, structured data.
So the full meal.
The full meal. You give it the input question, the full step-by-step reasoning trace, and the final answer. So the model spends all its time internalizing these detailed, complex, multi-step patterns. It learns how to connect the logical dots, explicitly.
So you're basically force-feeding the model the blueprint for brilliant thinking.
Exactly. It gets the full, expensive lesson. But then, and this is the key during inference, the thought-free phase, the researchers introduce a simple but incredibly effective constraint.
Which is?
They prompt the model with a completely empty reasoning context. It's compelled right from the start to skip the intermediate explanation and just output the final concise answer.
Hold on. If the model is forced to skip the explanation, doesn't it just become a glorified, less accurate standard prompt? Why wouldn't it lose the actual computation that led to the good answer?
That is the million-dollar question. And what's so fascinating here is the information theoretic rationale behind it.
Okay.
Standard explicit reasoning, your normal chain of thought, it acts as expansion. The input, the question, expands into this high bandwidth intermediate representation. That's the verbose reasoning trace before it hits the final answer.
Right.
3TF works because that intensive thought training aligns the model's internal reasoning and its answering mechanisms. Think of it like learning to play a complex piece of music.
Okay, I like this.
During practice, you are explicitly going through every note, every chord transition, slowly, deliberately. That's your explicit CT. But once you internalize it, when you actually perform, you don't have to consciously think about every single note. The structure, the sequencing, it becomes muscle memory.
I love that analogy, muscle memory for intelligence.
Precisely. Because that structure is internalized, when you suppress the textual output of the reasoning trace at inference, the underlying computation doesn't just vanish. The process transforms into controlled compression.
So it's still happening, just under the hood.
Exactly. The model executes the same latent structure directly into the final answer without verbalizing the steps. It successfully transforms reasoning from a visible, expensive linguistic process into a silent, efficient, latent cognitive one.
So the model is still doing the hard mental work. It's just learned how to compile that whole thought process into a single, concise result, saving us all those tokens and latency.
That's the theory.
And for us, the rubber hits the road with the numbers. Let's talk about that key trade-off. What price, in terms of accuracy, do we pay for this huge efficiency gain?
This is where 3TF really shines. When you look at the empirical evidence, it's pretty stunning. They tested this extensively on variants of the Quen3 model, comparing 3TF against the standard full-code thinking mode. Let's focus on the Quen3 14B variant on the GSM-8K math benchmark.
Right, a standard one.
So in the full thinking mode, the model is highly accurate. It achieves 94.6% accuracy, but it averages over 1,500 output tokens per solution.
1,500, wow.
Yeah. Now look at 3TF. The accuracy remains virtually identical at 94.4%.
So basically no drop.
Almost none. But here's the kicker. The model uses only 275 tokens.
Wait. 1,525 tokens down to 275. That is less than a fifth of the original output.
An 82% token reduction. And that isn't just a slight improvement. It fundamentally shifts the economics of deploying these models in high-traffic applications.
That's the difference between a system that crushes your budget and one that you can actually scale.
It really is.
So what about harder tasks? Does the fidelity of this implicit reasoning hold up when the math gets significantly tougher?
It does. The consistency is remarkable. On Match 500, which is a much harder set of problems, 3TF achieves 98.6% accuracy, compared to 98.8% for the full coupe.
A negligible drop of 0.2 percentage points.
Barely a rounding error, but the token output is again dramatically reduced. It's using only 43% of the tokens. So the model is still silent and accurate, even when the underlying task complexity goes way up.
Let's put this in context of those existing long-to-short baselines you mentioned earlier.
Yeah.
We know those methods try to fix the verbose output after the fact. How does 3TF stack up against them?
This comparison is crucial because it really validates the whole asymmetric training approach. Take prompt-based methods like just telling the model be concise.
Right.
They keep the accuracy high, sure, but they typically only achieve about a 43% token ratio on GSM-8K. That's still far too verbose compared to 3TF's 18%.
Still more than double the output.
And then you have methods that are designed for really aggressive compression, like something called CoT-valve. While they can achieve high compression, they suffer a significant performance drop. You sacrifice accuracy for that brevity.
I see.
3TF achieves a superior trade-off because it's foundational. It's internalizing the structure from the rich Housey training first, and then enforcing the concise output at inference.
Okay, that makes perfect sense. You train for richness, you deploy for economy. But let me introduce a skeptical note here. Aren't we just trading latency savings for, opaqueness? How can you trust the model's answer if you can't see its work, especially on mission-critical or, say, financial tasks?
That's a vital question. And what 3TF argues is that the quality of the answer is what matters, and that quality is retained because the internal process is so structured.
Okay.
And this leads us perfectly into the scaling laws, because model size seems to be the key factor in how reliably this internal structure is actually recovered.
And here's where it gets really interesting for me. The scaling phenomenon. This study looked at model sizes from 4 billion all the way up to 32 billion parameters.
Yeah.
We often think of reasoning as requiring these explicit steps. Does the capacity for this kind of silent, implicit reasoning just get better with sheer model size?
If we connect this finding to the broader trend of LLM development, the answer is a resounding yes. The data shows a clear monotonic trend.
What's the trend?
As the model scale increases from 4 billion parameters up to 32 billion, the performance gap between the 3TF mode, the no-think inference, and the base-think mode consistently narrows.
So the bigger the LLM's brain, the less it needs to scribble down its work to prove it's thinking effectively.
Precisely. It suggests that larger LLMs possess inherently stronger latent reasoning priors. They're simply better at internalizing and recovering that learned structure.
And the efficiency advantage.
It actually compounds with scale. When you deploy a 32 billion parameter model using 3TF, the relative drop in accuracy compared to the verbose version is minimal. You get massive efficiency benefits with almost no performance cost.
For anyone planning large-scale deployments, that's huge.
It is. It makes 3TF a really powerful paradigm for the scalable deployment of these large, cutting-edge, reasoning-capable models. The bigger the model you can afford to run, the more effective the silent thinking mechanism becomes.
Okay, let's move into some of the critical nuances here. Does 3TF strictly force the model into pure silence? Or does it allow for some, subtle adaptive level of self-correction?
It's definitely not pure silence, and the model exhibits this really interesting adaptive behavior based on the task difficulty.
Oh, so?
On the harder, more abstract and distribution-shifting benchmarks like Olympic and AMI-24, 3TF shows a slightly lower compression ratio than it does on the simpler GSM-8K.
So it produces slightly longer outputs.
Slightly longer, though still highly concise outputs. It seems to be doing that to maintain its accuracy.
That sounds a little counterintuitive. How can the model know to produce a slightly longer output if it's supposed to be in thought-free mode?
Well, it seems to go back to that internal alignment. When the model encounters a higher cognitive load, it appears to adaptively surface these minimal critical reasoning artifacts only when the task's complexity really demands it.
Okay, so what does that look like in practice?
If you analyze the output structure and compare it to a baseline pure no-think mode, where the model is just told, give the final answer, the 3TF model increases its use of what you could call reasoning markers.
Reasoning markers.
Yeah, subtle proxies, words like wait, however, or check. They are sparse, they're minimal, but they pop up more frequently on these complex tasks. It suggests the model is self-regulating its minimum necessary output just to ensure correctness.
That's fascinating. It's like a quiet cough or a small adjustment to ensure stability rather than a full monologue.
Exactly.
Now we come to what I think is the most crucial finding, the one that validates the whole asymmetric design, the danger of mixing data.
Ah, yes. Figure 4.
Because 3TF relies on this strict separation-rich training, constrained inference, a natural question is, why not just train the model on a mix of long Gautier answers and short final answers? Wouldn't that be the most comprehensive way to teach it both styles?
That was a key part of the research, and the answer is a definitive no. The results showed that if you include even an extremely small amount of no-think data, say, just 1% of your total data set during the main fine-tuning.
Just 1%.
Even just 1%. You fundamentally damage the model's capacity to internalize that deep structure.
Wow.
While mixing the data does successfully shorten the model's output, which is what you'd expect, it monotonically reduces accuracy across all the tested benchmarks.
Monotonically. So the more you mix in, the dumber it gets.
The more thought-free data you mix in, the worse the reasoning performance becomes. It's a direct negative correlation.
That is a brutal indictment of trying to dilute the training process. It confirms that you have to optimize for the richness of the Coty structure during training to achieve that internal muscle memory.
You have to.
You can't teach brilliance and conciseness simultaneously during fine-tuning. You have to teach brilliance first, then enforce suppression later.
Absolutely. The training must be pure. You train on the complexity, then you enforce the economy at inference.
So, what does this all mean for us? Let's take a final step back and summarize 3TF's contribution to the AI landscape.
I think 3TF provides a novel and exceptionally practical solution to the efficiency crisis in LLM reasoning. By cleverly decoupling the learning and the deployment phases, it shows that we can fully leverage the interpretability and performance benefits of chain of thought during development.
Without paying the price of deployment.
Right, without incurring those massive token and latency costs of verbose output when you actually need to use it. It really gives us the best of both worlds.
And while the efficiency gains are transformative, it is important to remember the limitations the researchers themselves noted.
Of course.
For example, the recovery of that latent reasoning is still notably lower on the smallest models they tested, like the Qwen 3.4b variant. Small models, it seems, still need to show more of their work.
That's right.
And critically, this framework has been primarily evaluated on mathematics benchmarks, AIM, GSM-8K, Math 500. So we still need wider investigation into how well this implicit reasoning translates to more diverse areas like common sense or summarization or dialogue.
Definitely. And this raises a really important question for you, the listener, to consider building on that muscle memory analogy.
Okay.
The fact that LLMs can internalize complex, multi-step structured reasoning and execute it without verbalizing the intermediate steps suggests that high-quality reasoning is fundamentally a latent capacity. It doesn't always have to be observable or verbalized to be effective. So what implications does this capacity for silent execution have for how we judge the depth of LLM intelligence if the best thinking is happening entirely behind the curtain?
A thought worth chewing on. Thank you for joining us on this deep dive into how LLMs are learning to be smarter and quieter at the same time. We'll see you next time.